All right, so let's get started. I'm really happy to one more time. Jason has been um, really nice to agree to give a lecture uh, now online, but still, uh, in some sense, I think it's even better because more of you are able to join. But yeah, I really happy here to have Dr. Jason Jerald, who has really been a partner of mine in with like different projects for maybe 3 or 4 years already. So it's really good to get Dr. Jerald to come and give this talk. He is a top expert in virtual reality in general. He is the CEO of Next Gen Interactions, which has provided virtual reality services to a lot of the high tech companies out there and government and a lot of different things. Jason's also a graduate of UNC Chapel Hill in computer science. He got his PhD there. So yeah, I'm gonna let you go ahead and talk a little more about yourself and tell us about what's good and what may not be so good about VR and what can we do to make it better.
Sure. Yeah, thanks, Hedges. So yeah, we're sort of injecting these realities into people's minds. What could possibly go wrong, right? So if you think about it that way, maybe it's not surprising that bad things might happen. And so, to understand what those challenges are as far as health effects goes, that's specifically what this talk will be about. And yeah, I'm curious, are you guys undergrads, graduate students, a combination of both, or what's sort of everyone's background?
Yeah, it's a combination. I'm an undergraduate.
Yeah.
Most of us are undergraduates.
Okay. Great. Well, that's really great to be able to have a VR class. I know when I was an undergraduate, there was no such class existed. So yeah, you guys are living in great times now. Doesn't mean there's not challenges though. There's also, this is specifically adverse health effects. There's certainly just other general, UX challenges as well, right? Which we won't go into, but yeah, one of many problems, but an important challenge is these health effects. If we're getting, individuals sick, or we're, give a demo to a reporter and they write up a story of how they got sick, right? That can't be good, not just for our projects, but for the entire industry. And so we should, take these things seriously. And my slides don't seem to be moving. There we go. Okay, so motion sickness is largely what this talk will be about, and is sort of, what most people think about when they think about health problems within virtual reality. But there certainly are others, such as eye strain, right? Your eyes can get sore. Some of you guys might have experienced this if you're looking at a screen, up close to your face, for multiple reasons, some of which are listed here. But then even outside of the headset, right? We can have physical fatigue, right? If your interface is up high, for example, then you're going to get tired, just like you would in the real world. And also physical injury, right? So not just getting sick, but physical trauma. And hygiene is certainly relevant today with COVID. And so having the proper protocols in place and such is certainly important. We'll primarily focus though on motion sickness because we can't cover it all. There's just too much to cover. And so what I think about, what I do in my book is I divide different factors into what I consider sort of the causes of VR sickness in groupings, right? Because there's so many to think about. And so there's quite a few here, but certainly this isn't meant to be all inclusive. But I divide them into system factors, individual factors, and application factors. By system factors, what I mean by that is something that the underlying system, such as the quality of the head-mounted display, right? Or is there latency in the system? Really not necessarily that we have control over as developers, unless you're creating the hardware, but things we need to be aware of. right? So if you have a wide field of view, for example, in your system, you actually can get more sick, right? We want that wider field of view because that's a more immersive experience, but it can actually be, because you're more sensitive to motion in the periphery, in some cases can, make it more sickness inducing. I also want to say we're not going to have time to go through each one of these, but I wanted to list these, to kind of point out that there's a whole lot to think about, and we can certainly go into, an individual item here, but just to kind of give you an idea, these are things to consider. And so if we're aware of those, as we start seeing problems, we can start thinking about them and, start investigating further on these individual challenges. By individuals, what I mean is, we're humans, and by the nature of humans, we're all different, we're all unique. And some people, react differently to these systems than others. And so, we really need to understand our target audience, right? So, how do those people, perceive technology? Are they prone to, regular physically induced motion sickness in the real world, right? Do they get sick on a boat? What are their beliefs? And it actually turns out that if you, are thinking about motion sickness, or you're thinking that you're going to get motion sickness, then you're more likely to get motion sickness, right? Or if you have sort of a model of how you expect the world to behave and it behaves differently than that, then that can be a cause as well. In some cases, we're just more sensitive to things, right? I know when I was a student, I did my dissertation on perception of latency. And what was really interesting, that was a surprise to me, is some individuals couldn't recognize, hundreds of milliseconds of latency. They just couldn't see it, no matter what I did to try to explain what they were looking for. Versus other, participants in the study were able to recognize, differences of latency down to 3 or 4 milliseconds. And so it really is, the individual is a huge factor, perhaps the biggest factor when it comes to, how prone we are to these problems. Now, as developers, the things that we have control over are these application factors. For example, how do we, if we are navigating through the world, how are we navigating through the world? Are there different techniques we can do to reduce that sense of motion through the world? How long are they in our experience? Are they, are experiences requiring the user to look around quickly versus just kind of, looking straight ahead, right? Those can make a difference. And so we'll be talking about some of these challenges throughout this talk. And please feel free to interrupt if you have any questions, or I prefer, interactive sessions. So yeah, feel free to speak up if you like.
So I do have one question about that previous
Absolutely.
slide, which is that hygiene is listed in the system category. So these columns are not, the majority of them do relate to motion sickness, but hygiene, I assume, does not. And so these are just kind of general. Okay, cool.
Yeah, and that's a good point. Hygiene could be also listed under the individual, right? Because what happens if the guy before you, hasn't taken a shower for 2 weeks? And so I wouldn't say, these are general, fitting in general categories. So yeah, this isn't necessarily the absolute truth. And that's a good point. This is more, I think most of these others largely relate to motion sickness, but not all of them, right? So I don't know, are you guys seeing my mouse cursor?
I cannot see your cursor, no. Oh, yes, I can, it's very small.
Okay, that was the other screen. So repetitive strain, right? So if you're using the controller just like a mouse, right? We can think about those things that your arms might get sore. So yeah, I wouldn't say these all are specific to motion sickness, but most of them are.
Could you briefly explain what the binocular occlusion conflict is?
Yeah, so that's one that's not talked about so much, but you can actually see it in some experiences where we see with 2 eyes, right? Well, most of us, not all humans, but most humans have 2 eyes. We have stereo vision, although a good portion of the population is stereo blind. But because we have 2 eyes, we can sense depth. But what happens if the way you're doing your rendering, that the stereoscopic image that you're creating, one image for the left eye, one image for the right eye, is not set up properly, or maybe it is set up properly, but as one object comes in front of the other, maybe I'm seeing it's not being occluded properly. So if I'm seeing through that, right, does this appear in 3D space behind the object or in front of the object? And so if you are doing your occlusion in an incorrect way, the stereoscopic cue might say that it's behind the object when the occlusion says it's in front of the object. So an example of this is with Steam VR, the chaperone system, right? Sometimes when they have that grid that comes up when you get close to a wall, you can, it appears in front of the a virtual object based on occlusion cues, but in stereoscopic cues, it appears behind the object. And so if you look at that closely, you kind of can see, you know, double vision, and it can be kind of really confusing what's going on, you know, visually, because your cues are in conflict there. And so it's sort of something hard to explain what that experience is, but if you look for it, it's a little bit subtle. It's not necessarily obvious unless you're looking for it, but it can be confusing.
No, that's helpful. In you know the research I have done, I haven't focused so much on the stereoscopic cues, but that at least gives me a pretty good idea. Thank you.
Yeah, and that relates to the vergence accommodation cues, right? That the way you focus on something, if your eyes are converging something right here, but the display, you know, the optics of your head mount are showing it 1 meter out, but your eyes are converging if it's right here, that can lead to headache. And so that actually gets to, leads nicely into the next couple slides of how the different sensory modalities, right? If they're not in compliance with each other, that's one of the causes of sickness. And so, yeah, we have different human senses, right? Kind of, you know, the ones we focus on are sight and hearing, and that's because those are, you know, super important. But there's also others, right? Physical touch. I know, you know, that's some of the research we'll look at next gen interactions is how can we have physical props and haptic feedback in the environment to, you know, in addition to the audio visual. And so that's, you know, a complete different problem. Proprioception is your sense of balance in the world, essentially. Well, depending how you think about it. So depending who you ask, right? Sometimes balance and physical motion is considered a subset of proprioception, or vice versa. Proprioception, the way I think about it actually, is your sense of where your body parts are located, right? So whether that's your sense of balance in your inner ear or my limbs, right? So if I reach out and I close my eyes, even though I can't see or hear my finger, I can still touch my nose. I have a pretty good idea of where things are. And so if that doesn't, you know, where you expect to physically feel with your sort of sense of where your joints and your body is located, if that doesn't match what you see visually, then that can be pretty confusing. And so, you know, how these different senses combine together, those multimodal perceptions, are really important for, you know, syncing those up in time and space. Otherwise, there can be a problem. So an example of that is latency in the system, right? If there's delay in the visuals, I'm physically moving my head, that's truly real time. But if the visuals delay are behind that, then what you see doesn't match what you feel with your moving your head around. That can be a major factor for motion sickness. Now, other things we can do, because, you know, we're making, you know, we're making up the rules with, you know, by creating these realities, is sensory substitution, right? So some things that in the real world are, you know, something you see or something you feel, you can give, you know, some, say, audio feedback when you reach out and touch something, even though you don't physically feel it. In some cases, you know, you can kind of, you know, at a sort of higher level, it almost feels like, you know, it adds some sensation of grabbing something, of just a buzzing sound, even if you don't have that haptics capability. And so perception is where to start with all of this. And so what I have here is I have Goldstein's iterative perception action process, who is Goldstein is a psychologist, nothing to do with VR, but it's really interesting to look at these perceptual processes in psychology and how they apply to virtual reality. And so this is a model of how distal stimuli out there in the world reaches our sensory receptors and then how we act upon them. And so, what we pay attention to is the attendant stimuli, and then the proximal stimuli is when it actually reaches the sensory receptors. And then we can act upon the world after it goes through these sort of, physiological processes in the brain, and we recognize those things. We can react those and change those stimuli out in the world. However, this is more than just a stimulus response iterative cycle. That is, we sort of have this top-down knowledge of being able to, that affects how we perceive the world. And so it's more a function of, the actual stimuli. It's how we think about the world. And that enables us to tweak the cycle and the world in a more conscious manner, right? Our beliefs and such. And so then what we do is we hijack the human's, perception system, and we create this thing, put this thing called a VR system in between action and that distal stimuli. And so that the human action becomes VR output, and the VR output becomes that distal stimuli. And in that sense, we're replacing real world distal stimuli with artificially created cues that the mind interprets as a form of reality. And then the system senses the user's actions and updates those stimuli. And as a result, the user experiences, what we call presence in this artificial world as if that world was real. And if we don't do that well, or we do things, differently than the real world, that can lead to the challenges. And so lots of things to think about from the psychology side of things, right? I think no better time than today of applying psychology because of what we have with virtual reality, right? It becomes absolutely essential. So even if you're a computer scientist, right, that's my background, to have a basic understanding or to be able to communicate with other psychologists is pretty essential to, understanding, to, building effective user experiences. And so here's some sort of, topics to list here. The point is not to go into these, but to, kind of point out there's a lot to think about as far as the psychology, not just the technology. And so, we could spend an entire course or an entire dissertation just on one of these topics alone. But the point here is that there's a lot to consider when designing for humans. So specific to motion sickness, there's sort of some 5 primary theories of why motion sickness occurs. And we'll go into, oh, I'm sorry, I'm ahead by a slide. Okay, not sure how that got out of sync there. But yeah, you guys should be seeing the slide, motion sickness, the basics. And so motion sickness, right? That's sort of the biggest problem. There's certainly these other things that are important to think about, but everyone should be thinking about motion sickness because we don't want people getting sick from their experiences, right? They're probably not going to give you a great review if you're creating an experience that makes them sick. And so when we do give demos, we want to be very careful to sort of observe our users and have them stop at the first sign of sickness, whether that's ourselves being the users or having other people being our users. You want to be well hydrated. I see some of you are drinking coffee or water, so that's good. Not hungry, right? Not hungover. That can be really bad. I definitely do not recommend that. And especially today with COVID, watch out for signs of colds, sinus congestion, etc. We don't want to remind our users to, we don't want to tell them, hey, just tough it out, you'll get through it. Because if they start feeling, they're not feeling well, the longer they go, the worse it's going to get. And so, let them know it's okay to take breaks and such. Wipe down the equipment, especially true with COVID, and focus on designing your interactions so that they're comfortable, right? And by that, not just in terms of are you, putting them on a roller coaster ride through an environment doing crazy things, but also just from a common sense sort of idea of don't have your interfaces in hard to reach areas and such. Make it comfortable for them. And one way to do that as far as motion sickness is to minimize accelerations, right? So actually constant velocity is actually typically okay, right? If they're moving in a constant speed in one direction, then most people aren't going to get sick. Might be a little bit uncomfortable for some people, but for the most part, that's okay. Virtual rotations can also be tough on some people. And of course, you want to keep your frame rate high, right? As you know, it's kind of commonly accepted now that we need to do that. But in the past, we weren't so good with that. One is because it was difficult to get, 10 years ago, it was difficult to get those high frame rates. But it's really easy to, not worry about that and have that as a secondary thing. Okay, here we go. So now we're on to motion sickness theories. Maybe first I should stop and take a break. Are there any other questions at this point?
Do you think a general, stable, static virtual reality experience, maybe like augmented reality or something like that, how damaging would it be for the eyes to, experience that for longer than an hour? Say you're reading a book or something in augmented reality.
Yeah, so augmented reality in many ways is motion sickness is much, much less of an issue because you have that real world, there's all, assuming your whole field of view isn't field, you sort of have a stable reference frame, which is the real world. And that actually relates here to this last theory, the rest frame hypothesis. We'll get into that, but essentially the real world serves as a rest frame. And this will make more sense when we get into that. But that's a really good point, that augmented reality, right? These are different technologies, right? So, it depends how you're building your hardware, how you're building your system can make a big difference.
I had a question about the wipe down the equipment. Does wiping down the equipment help? Is it like intended to give users a break? You stop them, wipe down the equipment, or is it that like clean equipment is more comfortable on your face and it's less hot, and so people are more comfortable, or is it just a hygiene thing?
I'd say it's largely for their protection, right? So there were cases in the past, documented cases of like people getting pink eye, right? Because the headset, the guy before them, had an infection. And so, yeah, that's for the protection of the user. But that's a good point. You want to be careful because if you're using alcoholic wipes and you immediately put it on your face, right, is that going to irritate some people's skin? And so there's always trade-offs here. That's something to consider. And so in some cases, for example, it kind of feels weird, if I'm getting something moist up against my skin, if you didn't know you're like, is that sweat? That's kind of gross, right? Some people might perceive it that way, even though maybe it's not gross. And so as an example of that, we would, in some cases, we have a fan going. So after wiping it down, we put the headset in front of the fan so, it can be dried off so it doesn't feel, wet on their faces. But yeah, primarily infections and, also psychologically, if you, a lot of people like, I don't want to put that on my face. I don't know whose face that has been on, right? Just seeing that these guys are serious about hygiene, they're wiping down equipment, I'm going to be more trusting. Another way we do that is, I think UNCG has one of these as a clean box technology that you put the device in a device and it floods it with ultraviolet light that has been, shown to, kill viruses and specifically COVID. I saw some of you shaking your head, so it sounds like you've used that device. That's probably better than wiping down equipment. Okay, so yeah, let's dig into an overview of these theories here. So the sensory conflict theory is the most widely accepted theory of motion sickness. And this is essentially what I was saying about those different cues, right? Not lining up. So the binocular occlusion conflict, right? If what you're, one cue, your eyes are telling you one thing, then, other cues from, occlusion is telling you something else, then it can be very confusing and can cause eye strain, right? Specifically for motion sickness, an example of what I mentioned about latency, right? Because what you're seeing doesn't match what your inner ear is telling you. And that mismatch in time can very much be a problem. That's one of the biggest causes of motion sickness, up to a certain level, right? As you start reducing the latency, it gets less and less. But if you throw a couple hundred milliseconds of latency in there, anyone that's in there more than, a minute or so is definitely going to feel that. And so that is the most, the most important conflict as far as motion sickness go, is that vestibular visual conflict. By vestibular, the vestibular organ in the inner ear that gives you that sense of acceleration and balance in space. And so essentially your eye sees movement, but your inner ear doesn't feel it. Or vice versa, right? You might feel, yourself moving forward, but then if the display doesn't update, there's a problem. And then there's the evolutionary theory, right? Why as humans do we get motion sickness? And so, properly perceiving ourselves and others and the world, that has been critical for us to be able to survive as a species. And if we get conflicting information, that means something, bad happened. We ate some bad berries or something. And so the brain interprets that sensory mismatch as a sign of intoxication, right? If you drink, too much of something. And so it's a protection mechanism, and it can trigger us to, eject that, what may have been bad material from our bodies. It may not have actually been bad material, but that's what we've been trained as, our species has been trained. If, weird things have happened, you might have, ingested something bad. So, let's get it out of our system. And so protection, right? Maybe you'll go into a fetal position if you start doing this, right? And so laying down till we recover, and that can be, helpful, right? Sitting down and relaxing if you're not feeling well from these experiences. Not just vomiting, but sweating, right? So you might start feeling hot in the headset, and not necessarily one way. If the headset's hot on your face, that's not going to help either, because you start feeling like something's wrong, and just isn't comfortable. And so the causing of nausea, it discourages us from doing those options again. Right? So not necessarily a bad thing that these, you're not feeling well. That's a good indicator that something isn't right. So this evolutionary or poison theory is great, because it kind of explains, but it doesn't necessarily give us actions we can take to, prevent it from happening. But it is, a good explanation of why it occurs. And then there is this postural instability theory. And this theory claims that we can predict sickness occurs when we don't have strategies for maintaining our balance, right? So the theory is, and this hasn't been proven, so this is largely a theory at this point, at least I haven't seen research, conclusively showing this statistically, is that the claim is you can actually determine someone's going to get sick by looking at how their body is moving before they actually get sick or before they realize they're getting sick. And so that sort of, how much their body is unstable is a predictor of that. And you can imagine, right, if I'm starting to feel dizzy, right, maybe I don't realize it yet, but, or I, want to lean up against something that isn't quite right because it's at the wrong angle or the wrong motion, then, your body's going to react in funny ways and start behaving, pushing up against something and realizing it's not there, pulling back, those sort of subtle sort of things might lead to sickness. And so if the scene's moving towards you, slowly towards you, you might sort of back up and lose your balance, right? That can be an indicator of something's not quite right. Or the inverse of that, you might lean forward instead of leaning back. And so you're going to become less balanced. The eye movement theory states that our eyes, the way they move, if they don't move the same way that they should in the real world, then that can lead to sickness, right? So for example, if I'm looking at an object out in the distance and it's behaving a little bit different than I expect, or let's say I'm looking at the world off in the distance, maybe that's probably a better example. I'm looking at the world and I expect the world to be stable relative to my head. And just to be clear, the world is not stable on your retina at all, right? As our eyes move around, we perceive the world to be stable, but the actual image on our retina is moving all over the place. But because, ever since we were born, we've learned, subconsciously to perceive the world to be stable based on the eye muscles are directly connected to sort of our interpretation of what we expect. And so if that doesn't match up what we expect because the world's, sort of moving in a funny way because of latency or whatever, then that can lead to motion sickness. And to go into more, specifics of that, of the eye muscles, we essentially afferent or sort of outgoing nerve impulses. I'm sorry, afferent is going inwards. So from the sensory receptors inwards towards the central nervous systems, those are afferent nerve impulses. And then efferent nerve impulses travel from the central nervous system outwards towards the effectors like the muscles and such. And efferent's copy, you can see here, goes to this sort of conceptual concept of the brain needs to compare the outgoing messages to the incoming messages, and do they match up? And if they don't match up in the way that's expected, then something's wrong. And so the brain says, what's going on here? And doesn't perceive things correctly and potentially gets sick.
And so the only typical reason that would occur is because of latency, you said? Because that kind of seems like kind of a strange problem to have for any other reason. I don't know.
I'm sorry, strange reason in what sense?
Well, it seems like I can imagine how latency could cause it, because as you're moving your head, you're looking around and things aren't quite where they're supposed to be. But it seems like you'd have to almost design a system intentionally poorly to cause that effect without latency problems, for reasons other than latency.
You're saying if latency was perfect, could there be other problems?
Yeah, and that's kind of uncommon for it to be other problems than latency causing this issue.
Yeah, let's say, for example, if your tracking is off, right? If you have distortion in your track space, right? And I move my head around and the world's distorting in some strange way because tracking isn't perfect, right? So that would be, sort of a system level factor that could be a problem.
Okay,
or
cool. I didn't think about
your, your scale or, doesn't necessarily match up, or your rotations, right? You rotate your head 90 degrees and, the world rotates 45 degrees, right? Which, some people have done that, right? Because there's advantages of moving your head a little bit. You can kind of see to the right, right? You don't have to look completely around you, but that can be, really sickness inducing. So yeah, it gets back to the design, but also the system factors. They all come into play. Okay, now to the rest frame rest frame hypothesis, which is consistent with the question about augmented reality, right? Where I said, the real world is a reference frame, a rest frame. And so this theory says that sickness results from conflicting frames of reference, right? So the rest frame is what we expect to be stable, right? In the augmented reality case, we expect the real world to be stable. In the VR case, we expect this sort of virtual world to be stable, right? And if that doesn't match our expectations of being stable, then motion sickness can be a problem because it doesn't really match our expectations of what is stable. And so it's not actually necessarily the case that the entire scene, at least according to this theory, the entire scene does not necessarily need to be stable. Only the parts of the scene that we expect to be stable, those need to actually be stable. So it kind of gets to our mental model of what is supposed to be stable, right? So for example, and again, this is, sort of a hypothesis, right? This isn't necessarily the truth. But if you have something that is stable, such as a cockpit here, as we have in the game Eve Valkyrie by CCP Games, if that cockpit is stable, then the outside world is something you're traveling through, then maybe that helps reduce motion sickness, right? Only part of the scene is unstable. Now, it's a bit of a contradictory claim here, because you kind of expect if I'm in the cockpit, then the cockpit is actually not stable, the world's stable, and thus, the cockpit should be moving. I should be feeling the cockpit. So it's kind of the inverse way of how we naturally behave in the world. But then again, it comes back to the mental model. If you think of the cockpit as stable, even though it's a little bit different than the real world, if your mental model is what's going on, that instead the world's moving towards you, then maybe that's okay. So for example, if you were to, grab the world, let's say it's a world in miniature, for example, and move it towards you, that could be something that's maybe not a problem. Or another example I sometimes use, if you have in the real world, let's say you have a really large door, like a barn door, right? If you grab that barn door and it's largely taking up your all of your vision, and you grab that door and you move it close to you, you're probably not going to get sick, even though your entire, most of your vision is saying everything's moving towards me, my entire visual field. You expect that barn door to move towards you. And because you have that expectation that, oh, it doesn't need to be stable, then you're okay. And so these theories kind of all tie together as far as, some of them apply to some cases, but not other cases. And a lot of this rest frame theory is sort of what is your mental model, what you expect to move versus what you don't expect to move. So it might be the case that we can train ourselves, even if it doesn't match the real world, if we train ourselves to expect some things to be rest frames, then if we design the experience and the experience matches that expectations, what you've been trained to, maybe there's less likely to get sick.
Do you have any idea, because it's not related to motion sickness, but how about headaches and migraines? Do you have an idea what is caused?
Yeah, absolutely. So, there's obviously there can be, different reasons why people get migraines, headaches and such, but a large part of that is eye strain, right? So it can be as simple as the brightness of the display. It could be the conflicts I talked about, for example, the occlusion conflict, right? Your stereoscopic does not necessarily match occlusion. It can be the accommodation divergence conflict of your eyes, are looking inward, but the focus of your eyes is saying it's way off in the distance, right? Those conflicting cues can cause, can be a major cause of migraines that sometimes people get when they're in VR for a while.
Are some color schemes worse or better than others at preventing or inflicting motion sickness?
Yeah, that's a good question. Not that I'm aware of.
Because I think of like that old like red schemed Game Boy Virtual thing that was really horrible.
Really bright, yeah.
Yeah, that's probably a bad choice in color scheme, but I don't know if there's any good ones or.
Yeah, well, so dark adaptation, right? How we, if you use red lights, right? If your alarm clock's red, right, it's going to, allow you to go to sleep more easily, right? Because your eyes adapt to, are not affected as much by the color red. And so that's certainly possible. In fact, there's, if you dark adapt, then it takes signals longer to reach your brain, right? So if you're using red color, you could maybe, it's complete speculation, but it might be the case that, latency is less of a problem with reds, right? Because it takes longer to reach your brain, or it could be worse, right? Because it takes longer to drain. It's sort of this real world additional latency. Now, what I don't have an answer for, if that's true, right? Which the literature says it is true, that if you're dark adapted, it takes longer for signals to reach the brain, then why don't we get sick in the real world if we're in a red environment? We don't. And I don't understand why, because in theory, we should be getting sick if we go into, a red room, right, versus a blue room. And so I don't have a good answer for that, but I think that would be a very interesting research topic. In fact, there's some interesting illusions that if you dark adapt one eye and not the other, and then swing a pendulum that goes, straight in front of you, it's not going in a circle. If one eye is dark adapted, because one eye is delayed, the pendulum appears to go in an arc because one eye perceives it later, and thus it lags slightly behind. And so one eye sees it a little bit to the left of the other one as it moves around, which implies you should get sick if you're dark adapted. So often the answers when it comes to virtual reality, or psychology in general, I guess, is more questions than answers. which is one reason it makes this field so exciting, right? It's going to be quite a while, if ever, that we get all the answers. There's yeah, it makes it an interesting, exciting field. Lots to discover.
So you're also saying that like some people can process like certain frame rates faster than others. Did you ever investigate if that has any effect on motion sickness or correlation?
What I did for my dissertation was specifically only perception of latency, not specifically motion sickness. And that's an interesting question, right? Just because you don't perceive it doesn't necessarily mean you won't get sick. So it might be that, I don't perceive it, but I still get just as sick as someone that, can easily perceive it. And so, yeah, you had another great question there. I don't know of anyone that's researched that. I do know, for example, pilots, right? Someone that has a really good perceptual understanding of what's expected may get sick in different ways, or more or less likely than those that don't know the difference. So right, pilots in a flight simulator, because they know exactly what's supposed to happen with the world, may get sick, versus a naive user that's just going along for the ride, doesn't know what he's looking at, may not get sick.
So would that be similar for like a basic thing like swimming too? Like if someone can't swim, like they wouldn't really know what to expect if you're trying to.
Yeah, very well, maybe. Or you say you design a swimming interface, right? Maybe that works for a swimmer, or maybe it's worse for a swimmer. I don't know. Yeah. I think one, an example, maybe a better, common example is being on a boat, right? If, you know to look out at the horizon because that horizon is stable. Essentially, it's a rest frame like we're talking here. We expect the horizon to be stable, but we don't expect, if we look down, the floor of the boat to be stable relative to our inner ear, right? So that's an example of someone with, experienced sea legs, because, he's more used to it, but also he knows to look off, to the horizon. In fact, there's a patent done by, I believe it's Tom Furness, out of one of the grandfathers of virtual reality, created the virtual reality systems back in the 1960s, right? Late 1960s, is he has a patent that creates a stabilized reference rest frame in the bottom of a boat. And the idea is, if you look at that rest frame that is stable, that acts essentially like the horizon, it's basically a fake horizon. If you look at that, the idea is you get less sick because you're looking at that rest frame. And if you expect that to be stable, maybe that can help reduce motion sickness. So another example of some rest frames is with this world-renowned researcher here. His name's Hedges Copper. Maybe some of you guys have heard of him. And then his student, Zekin, at Duke University. I believe he may occasionally be on the UNCG campus. Is that correct, Hedges?
Yeah, well, now nobody's at UNCG,
Yeah.
but yeah, he is doing his research at UNCG now.
Okay. So yeah, continuing that research, and also, well, I guess I'm missing a slide here. I was hoping to go into that. So we may come back to that. But the point is, if you're interested in this research, your people, the experts are, they're at the university. So you got the right people. Okay, so this is sort of a model I adapted from Razak's dissertation on redirected walking, of the model, the mental model of how the world works, how we perceive the world, specific to motion sickness. And so, those are all theories that we had previously, but as typical in life, there's usually not, one theory that explains everything. It's sort of, these bits and pieces, and it's a combination of theory. And so this kind of brings things together with the idea that motion sickness is not caused by one thing, but very likely a combination of these different things. And so our mental model, the state of the world, our actions, these all contribute to motion sickness, right? And so I tried making this consistent with those 5 theories. so that we, for example, have eye movement, right? That efference copy, that prediction of where our eyes are going to be and where we expect the image, even, subconsciously, where that image is to be. And so that is the action of the eye movement feeding back into the central processing of the brain, as well as that action being fed back into the environment, being the actual display, as well as the vestibular sense of our head moving, feeding back into that. And then we have our mental model, which is largely part of that anyways, is the rest frame, right? What do we expect to be stable? And all of those, if those all feed in and are consistent, then there'd be minimal motion sickness. But if one of these things go wrong, the visuals isn't quite right, then those things don't match up, and there's going to be a problem. The brain's going to get confused, and it's going to eject what it think might be toxins from the body. And so an example of this is a lot of examples. So let me try a couple. Maybe real world exercise I like to give is how we expect the world to move, right? So our eyeballs, I mentioned, we're moving around, but we still perceive the world to be stable because we have that efference and afference, right? If they don't match up, then something's wrong. And so our muscles are directly connected to those expectations. As I move my eyeballs around, because the muscles are moving the eyeballs, I expect the image on my retina to move to match the opposite of what my muscles tell the image on my retina to do. However, if it's an external force acting on the eye, then your brain doesn't know about that. So an example, and you want to obviously be careful with this, but if you give just a slight amount of, if you close one eye and give a slight amount of pressure on the eye, because the brain isn't used to some external force, being your finger in this case, pushing on the eye, then the world feels like it moves. And it also feels just very slightly, at least for me, slightly nauseating, right? But it's just a movement. Why is the difference between my finger and a muscle? Well, because the brain knows about my eye muscles, but it doesn't take into account my finger muscles, right? So that's an example of these things coming together as far as the expected motion and the eye motion theory of motion sickness. Another example is if you're in the back seat of a car, right? If you're reading a book, some people get motion sickness, right? Because they're feeling their head jostling around, but the book is sort of stable, right? So, but if you look out the window, then the outside world, your expectation is that is stable. Oh, I get it, I'm moving. And the outside world is what is stable. And then related to that is it turns out drivers don't get as sick as passengers because they have that sort of locus of control of being able to control where the car is at and what to expect, right? If they turn the wheel, they know to expect the car to move rotate to the left. Whereas the passengers, if they're not expecting that, it doesn't match their expectations and thus they'll get sick. So it's sort of, these different theories really do sort of explain what can go wrong, but also can, give us clues of, how to come up with, new ways to navigate through your spaces. Again, more questions than answers, but, at least this is a starting point. And so that leads to some examples, right? So optimizing adaptation, right? That is slowly have the user adapt until they get to, come to an understanding what to expect. Don't, throw them in the crazy, roller coaster rides at first, but, after a while you may come, you sort of adapt to virtual reality, right? You can use real world stabilized cues in your environment, which is some of the research that Dr. Copper has been doing. Manipulating the world as an object, right? I mentioned the barn door, but what if we could, reach out and grab the world and move it around? It's this big object around us. And if you can induce that mental model in to the user, maybe, that's a way of navigation, sort of grabbing the world. Leading indicators, examples of that are giving you a clue of telling you what the expected motion is going to be before it happens, right? So having, a directional arrow in front of you that points in the direction you're going to move, a little bit later. That's been shown to work. Mentioned minimizing visual accelerations and turning, right? helps a huge amount where constant velocities are okay. Ratcheting is something from Cloudhead Games, right? Instead of having this motion, what if you have sudden turns of clicking by, 20, 25 degrees or so, or whatever it might be. Instead of the motion that's the problem, you sort of have this instantaneous changes, sort of like teleportation, right? Having these jumping to new locations instead of having that sense of motion through the world, you instantaneously jump. And of course, real walking, right? If we have unlimited tracked space, then ideally you don't need to do any, crazy forms of navigation through your virtual environment. However, even then, right, if I want to go to the other side of the world, I don't want to have, if I want to visit another country in VR, I don't want to necessarily, even if, the whole world was perfectly tracked, I don't want to physically walk that entire distance. So even if you do have large tracked spaces, that you don't necessarily want to do that. You might want to use teleportation. You might want to do these different things. What I have listed here is these dynamic field of view, dynamic rest frames, which is what Dr. Copper has been looking at. And I think given the time, I might go straight ahead. I think you guys get the basic idea of, teleportation and such. So I don't think we need to necessarily go into, how those things work. So dynamic field of view, the idea here is that we're more sensitive to a couple things. One, we're more sensitive to motion in our peripheral, right? That's how the eyeballs work. But also just, if less things are moving, no matter where it is on the eyeball, the less likely you are to get sick, right? You think of going to the extreme of if I close my eyes, then, I'm probably not going to get as sick, right? Because there's not that sensory conflict of what you're seeing versus what you're feeling. And so, if you don't go all the way, you don't close the eyes, but you reduce the number of pixels that are moving on the screen, that might help. That's some rest frames. This is an example of rest frames we're looking at. If these arrows serve as stable cues that match the real world, even though the world is moving, right? So if you think of these arrows, it's hard to see here without actually experiencing it. But if these arrows were actually attached to the real world tracking, right? The real world, room that you're in, and the rest of the world is moving. What if you focus on these arrows? Would that result in less motion sickness if you think of those arrows as being stabilized to the physical world, right? As sort of, those being locked to the real world. Sort of the early preliminary results were not conclusive. We weren't seeing a big difference. So that's an example of something, it might work, might not work. You sort of need to experience it. I think maybe one of the reasons why it didn't work is it was sort of hard to explain that concept to a user. It might be after they really do get the concept versus, someone trying it for the first time, maybe it reduces sickness. We don't know. We didn't really explore further than that. But that would be something to look at, and something Dr. Copper has been looking at. Sort of not related to motion sickness is just, when you get close to a wall, right? This is the chaperones, similar to chaperone system you see with HTC Vive. So if you try that, you probably, we don't need to go into details on that. It protects you. If you get too close to something dangerous, let the user know. Okay, so what we have here is a combination of narrowing that field of view along with the concept of the static rest frame. The rest frame here being a cockpit, right? Similar to the Eve Valkyrie screenshot I shown earlier. Has anyone tried that game, by the way, Eve Valkyrie? It was an early game that was supported by Oculus when the Oculus came out, but it was a great experience, especially in the early days. But essentially, it was that stabilized cockpit that, they didn't call it a rest frame, but essentially that cockpit behaved as if it was stable in the real world. So that part of the scene was at least stable. And so in this case, we're kind of doing the same thing of this sort of, this futuristic cockpit that you're, inside of to navigate through the world. And then when you navigate through the world, we increase the size of that rest frame, which also serves to reduce the field of view. So when you're perfectly stable, you can see more of the world out through the windshield. But then as you move, we fog up the windshield, so you're seeing less motion, right? And there's trade-offs here because you sort of have less situational awareness because you see less, but the idea is as you're moving, have less motion. And so this is kind of really weird to think about, right? This is not how the real world thinks of it, is how it works. But when we're creating these these interfaces that might or might not be effective, but we're experimenting, how do we make that sense, make sense to the user? And so how we do that? Well, we get to be creative, right? These abstract interfaces, we you can start thinking about how could we actually incorporate this into the story of our games or our applications, I should say. And so I have a video of an example of that. And so here how we had this really weird interface sort of, fitting in with the story being that you're a, you're a contractor many years in the future, and you put on your virtual reality headset to drive your drone through the world to fight the bad guys, and the bad guys being the aliens. So it gives a reason to put on the headset, and then we slowly introduce these weird interfaces. And the reason we have that interface is to prevent motion sickness, because you have a head-mounted display on. So, telling it sort of like it is and having it fit the story. And so this is an example of a rest frame. It's sort of hard to describe, but hopefully this sort of explain will kind of give a clue of what it is. And so I don't think you're hearing the audio here, so maybe I'll just explain. You're inside a cockpit to start with. You select your scene, and now the stabilized scene, you're going to travel on your drone through the environment, but that drone is stable relative to the real world.
And so the assumption is that since it's tied in with the story of the game, users can understand how it will behave better, and so it's more effective at preventing motion sickness?
Yeah, to sort of have it more so make sense, right? Versus this abstract, what the heck is going on here? Like, why am I in this bubble? Sort of thing, and explaining the reason for the interface, right? So kind of building up that mental model of what to expect. Otherwise, it's just strange. And so sort of understanding, and as part of that tutorial of explaining the weirdness to start building up their mental model. And sorry you guys can't hear the audio there. It's not very effective if you can't hear that audio.
I don't know if it makes sense, but you could, if you stop sharing, you can select a share audio.
How do I do that?
So stop the share.
Oh, I see. Yeah, part of the problem.
Then when you share again, the lower left, there will be an option to share the audio.
Under audio settings, or which one?
No, when you open your share screen to select the screen that you want to share, at the lower left of the selection window, share sound.
Excellent. Yeah, I found that. Thank you. Wasn't aware of that. Okay, so let's try again. Okay, you guys seeing the screen again?
I don't think you shared it yet.
I can't see it.
Oh, sorry. That would be helpful. Okay, how about now?
Mm-hmm. We are seeing the like 2 slides now. Like the current and next.
Screen. Let me try that again. Okay, single slide now?
Yeah.
Okay, so there's an asset out there that kind of does this concept, and this sort of is another example of how to use rest frames. So I'll go ahead and play this guy. Hopefully you guys can hear it.
I'm going to briefly explain tunneling, go through the example scene that we include in the package, and go over some of the major features. So what is tunneling, and why do you want it in your projects? Many VR players experience sim sickness. This is generally caused by a mismatch between what you see in the HMD and what you feel in real life. In short, this is caused by artificial locomotion. Tunneling is a powerful way to mitigate this effect. The brain gets a large amount of motion data from peripheral vision. When artificial locomotion is detected, tunneling dynamically reduces peripheral vision, and in doing so, reduces the sense of motion. While this looks very intrusive on screen, it's actually quite subtle in the HMD. There are multiple ways of achieving this, and VR Tunneling Pro gives you a wide set of options. We'll explore these a little later on.
Okay, so that kind of gives you maybe a little bit, I think maybe explains it a little bit better. something you sort of have to experience. I know like Google Earth at one point, I don't know if they do currently, but they had like a grid fade in that acted as a rest frame, right? So as you move, it brings in something stable relative to the real world, which would reduce sickness. Okay, so the point of these things is there's a lot more unknowns than knowns, right? Certainly the knowns are a great place to start, but we have to, did you guys lose my screen again?
Yes. We see your click up. There you go.
Okay, better. Okay, there's really very few universal truths that work in all cases. Yeah, there's a few, like you need to keep a good high frame rate. You need to have good quality tracking, those sort of things. But there's a lot to think about, a lot to consider, and you don't know until you give it a try. And so you have to design, you have to experiment, not just on yourself, but remember the individual is a huge factor. So, you might be immune to motion sickness, but, because you've used VR a lot. And so you want to try it on your friends, ideally you'll have, formal user studies, all of that. There's a lot to try here, because what will work in theory might seem like a great idea, but you don't know until you try it. And so there is something that's common to all VR development, and that is iteration, right? Of, you sort of have to, figure out what you're going to do, then go make it, and then learn from it. And so, constant learning is what VR is all about. Again, one of the things that I love, that there's always something to learn here. What else is common is sort of these universal guidelines. You want to create, you want to, have your system so it's low latency, but also your application, right? The system, if it's a great system, it doesn't automatically, solve everything. You can still have, an application that isn't optimized. You want to keep that frame rate at the refresh rate of the display, or even higher. In some cases, depending how you configure your hardware and such, you can have advantages of going even higher than what the display can handle. And if not, fade out the world, right? So that's one thing I love about Steam VR, is they automatically fade out the world when things get bad. And so I think that's a great protection mechanism. Solid head tracking and minimize virtual rotations and accelerations. I think these are, things that are kind of, we all should keep in mind. The other things is, a lot more complex, a lot more to think about, and not as much known, that are more experimental. But these are pretty well accepted. And then there's a question of, okay, you try it on your friend, right? But that's sort of a subjective measure of, did they, were they sick, right? Just by asking them if they're sick, that can be a problem, because you're implying that they're sick. Then they think about, oh, maybe I am sick. And they might answer yes when they weren't. And so there's, different advantages of, how you ask questions, right? Leading the participant with questions and such can lead them to thinking that. And that's actually been documented and researched, that if you tell people at the beginning of their experience that you might get sick, or specifically if you say, take this sickness questionnaire, just by giving them a sickness questionnaire can suggest to them that they will get sick. And it's been shown by giving a sickness questionnaire at the beginning of the experience, they actually report getting sick, right? Less so than if you don't give the questionnaire. And so there's all these very subtle, things to consider when you're trying to determine if something causes sickness or not. So the Kennedy Simulator Sickness Questionnaire is sort of the standard standard questionnaire that is used, and it looks at these things, these specific, causes of discomfort or sickness. One of you asked about headaches and eye strain, right? That's they happen to put that under disorientation. Not sure why they put it in that category, but that's the way that's where they put that. And so, difficulty focusing, right? Those things are often due to problems with the visual display. And that kind of gives you a clue. Okay, maybe that's something about the display, not necessarily latency. Although it sort of, gives you a way to think about, giving you some clues of, how do these all relate together? And so this is the standard, but there are problems. So I mentioned the point about pilots, right? Maybe reporting, being more sensitive to simulator sickness. are to these adverse health effects. Well, if you look at the questionnaires, pilots actually report in simulators less motion sickness, not more. Well, why do they report less? Well, because if they report being sick, they're likely to be grounded. And so they may be getting sick, but they're not going to admit it, right? Because they don't want to be grounded. And so that's an example of, sort of a problem with questionnaires. In this case, the three factors that we discussed that can, have adverse effects, system, individual, and the design or the application. Well, the Kennedy Simulator Sickness Questionnaire, one, is not designed for head-mounted displays. What they looked at for the Simulator Sickness Questionnaire was flight simulators, projected screens, sort of simulators, not head-mounted displays. And so this was not even designed for head-mounted displays. We just use it for head-mounted displays. That's sort of a problem. The pilots, right? The putting into categories and the measurement how sick you were getting was based off of the participants being pilots, right? So it was a complete different audience, right? So they may or may not get sick in different ways, but that's how the questionnaire was designed. And it was also designed for not just the physical hardware of flight simulators, but you're moving through the world as if you're in an airplane, right? Not necessarily doing different things. So this Kennedy Simulator Sickness Questionnaire was not designed for virtual reality, head-mounted display type of virtual reality. So my argument is, it's useful to collect this, but this is not the ideal way to measure sickness. It just wasn't designed for it. We reuse it because it's convenient. There's also a huge variance with the Kennedy Simulator Sickness Questionnaire that, and there isn't a threshold of, you are sick, you're not sick. It's not well defined. And it's biased, right? Based off of, I don't want to admit to being sick, right? So other ways of doing things beyond questionnaires are physiological measures, right? So, does their heart rate go up? Does their palm sweat increase? Does their forehead, moist, right? Those sort of things might be a way to measure sickness. This is sort of an open area. There's claims on this, but lots of areas to research in this to, prove this is a direct sign versus, just a, potential indicator or correlation. Other things like postural stability. I talked about that not yet being proven, right? If I start swaying and moving around in a funny way by, using an inertial sensor on the head, that might be a clue of people getting sick or not. Eye tracking for the eye movement theory of sickness, right? I haven't seen a lot of research as far as, how the eyes behave differently in VR because there's more latency or whatever in the system. I think that'd be an interesting topic. I'll send out these slides later if you want. You can sort of see some other example questionnaires. One study I love is the Fernandez and Feiner study of they just ask them straight up in the experience. It's not a questionnaire after you've done the entire experience, but just asking the user, right? It's sort of intrusive. It's going to break presence, but straight up, how do you feel on a scale of 0 to 1? And so these straightforward solutions, I think, are a great way to collect data. Simple can be better. It doesn't solve everything, right? Users might still be biased and such. There's no perfect way to measure sickness, but I do like this approach personally. And so what they did in this study is they looked at that dynamic field of view, right? If as you move, you narrow the field of view, and then when you stop moving, you see everything. And so that's what they looked at. And so they have what you call restrictors, which no restrictors mean as you move, you don't narrow the field of view. Restrictors means you narrow the field of view as they move. And so here on the y-axis, we have the discomfort score. That is, are they not feeling well? 10 being, worse. You can see, as expected, the longer you're in these experiences, the more uncomfortable, right? That's pretty much widely accepted if you're, have any sort of motion in the world. And then when they don't have those restrictors, when they do have the restrictors, it's better, right? There's less discomfort. So that green line is the average of these individual points of people saying on that scale of 1 to 10, how uncomfortable are you feeling? And so it makes sense, right? Not having restrictors. Yeah, okay, restrictors makes a difference. Let's use them. So what we would expect. By the way, Hedges, have you had your students look at this paper?
No.
Okay.
Yeah.
So yeah, this is a really interesting, fascinating paper, I think. So that is essentially looking at those, narrowing the field of view. And so that kind of makes sense. There's nothing surprising about that. However, if we dig a little bit deeper, here we ask, does order matter, right? So what if they do not have these restrictors the first time, right? But then they go in a second time and they do have the restrictors, right? Now the field of view, is narrowing, then kind of makes sense that the second time it still is less discomfort, right? Because the first time I was had no restrictors, and now I do it a second time, I have restrictors, it matters. Whereas here on the top, it was between subjects. So it was the first time someone experiences it, they only experience one of the conditions, not both. But what if they experience one condition first? And so again, this is sort of what's expected, right? But what's interesting is when we do restrictors first and then remove the restrictors after they did have the restrictors. And this is what was surprising and really interesting, is now that they've had a chance to experience with restrictors, now they go in with no restrictors and suddenly they're more comfortable. And so one of the questions is, not completely conclusive, but is it the case that you could train with these restrictors and then remove the restrictors, and now I've adapted better? Now I'm okay, right? Because I tried it for a few minutes with the restrictors. And so that was the interesting result and surprising result of that paper. And if you look at it from this in this slide, it puts all the data together, right? When they had no restrictors first, and then they had the restrictors second, right? You can see there's a big jump, right? But then here, when they had the restrictors first, that was actually better than doing the restrictors second. But then when they did the restrictors second, then it got even better. Some challenges with this study, right? Again, this isn't completely conclusive. You might look at this data and say, well, what if we want to have more a control group of restrictors first and restrictors again the second time, right? Is it just a matter of just because they've been in the experience longer? It might be with restrictors second, we might have a line further down here that's even better. And so again, often research leads to more questions than answers. I think that's about 1 hour and 15 minutes.
Yeah, we're at our time. Well, good. Yeah, we can go over a few minutes just for your conclusion.
Yeah, conclusion is we know a lot about VR sickness. However, we don't understand a lot about VR sickness. So again, a wide open field that, expect to do lots of experimentation, lots of iteration, not just on yourself, but, others. And then, also eventually, right, that's the point of research if you're going into, graduate school and such, to, if you're really interested in true answers of statistical analysis and not just, biases of people, being subjective in their opinions, really getting to the truth, then I think that's an exciting research area. Any questions?
Great. Yeah, thank you so much, Jason. I'm happy that there were questions throughout the talk, but that limited the time now. But if you have a few minutes to stick around if others have questions, then yeah, if anybody has any question, go ahead.
Absolutely.
In that particular study that you were just referencing, did they say how long between the experiences they tested out?
As far as taking a break?
Yeah, like was it immediately after they tried the narrowing the field of vision that they immediately switched to not doing it? Or like did they take the headset off and take a break? Or
I believe, and Hedges can correct me. So it's been a long time since I read that paper. So but I believe they came in on a different day. Do you remember if that
Yeah.
was?
Yeah,
Oh,
it was days
really?
apart. Yeah.
Oh,
So yeah,
very
they were
cool.
completely rested. And that's a great question, because if you did it immediately, that would imply I basically just had a longer session with, a very brief break, that you're likely to, just continue getting sicker, right? Because you only took a very short break.
Yeah, and sickness is additive, right? You don't you need time to recover, and that's right.
Yeah, in that case, it might have been the opposite effect. Instead of people getting better the second time, right? They might have, they probably would have gotten a lot worse the second time.
Yeah, another thing that's also, so you talked about other control groups. I think with this study particular, and a follow-up study that we did, you and I and Zekun, that looked at rest frames, but on the same type of thing, we got the same results. But what's still to be known, but hasn't been done, is whether there is just a general adaptation. That if you did the first and second trials without any assistance, are you gonna feel better the second time around regardless? And that's one thing that's not is not yet known.
Yeah. And that could nullify their claims, right? It's just, well, they adapted.
And hours.
And so, yeah, you always want to question these, poke holes in things, right? And figure out, okay, how can we investigate that further? Again, often this type of research leads to more questions than answers.
So you mentioned that there's some few always best practices, few universal truths. But you said by and large a lot of this stuff is kind of application dependent. Are there any in your consulting work, has there been any notable times where you had very difficult, very, very hard at odds, goals for the application versus trying to balance motion sickness that you had to notably overcome somehow?
As far as balancing off different trade-offs?
Particularly for functionality versus motion sickness.
Absolutely. And so, ideally you just never move, right? And then if you have, low latency, a good tracking system, you might have, sort of minor, problems, but for the most part, it works really well. But then you can't do much, right? What if you want to navigate? You can teleport, but there's limit, teleportation, some people don't like, right? Because you don't feel, some people say they don't feel as present because, it kind of makes you lazy of just pushing buttons, right? Instead of physically walking to have you feel more present. And so there are always trade-offs, absolutely. And it also gets to your audience, right? If you're creating a game and your target audience is hardcore VR gamers, then it might be the case that you identify your audience that these guys have been doing VR for years. They're fully adapted. These guys aren't going to get sick, right? Or 99% of, our target audience is going to get sick. In that case, you can get away with, more motion. You're not as concerned about it. And so some game developers have done that. It's not like they're naive and, don't understand sickness. It's that they've been doing it a while. They understand it and they're willing to make those trade-offs. So yeah, it's always a balancing act. Always trade-offs.
All right, thank you.
And so, yeah, I don't think the goal is necessary, depending what you're trying to achieve, the goal isn't to, or I shouldn't say the number one goal, right? It's all about priorities. Maybe that's not a priority for some applications. It should definitely consider it. But, if you have to have, redirected walking, for example, if you need that, the answer is never do, if it was truly motion sickness, you'd say never do, that technique.
Okay, thank you.
All right. Well, thank you again, Jason. It was great. I'm sure that everybody learned a lot, and I have a lot of new questions in their minds, which I think is good. But yeah, a lot of this is also being critical about what has been done and how it can be improved. And we'll never. The goal is to answer one question and open another 10, and there we go. We always expand. But yeah, thank you so much.